Okay, so today's class is essentially all about common distributions. So we'll do a couple of the remaining ones, discrete distributions, geometric, which I forgot about last time. Then go back to Poisson. I'll spend some amount of time on Poisson. They will cover Poisson in much more detail when you do queuing theory, because it turns out Poisson is much more relevant there. So we'll come back to Poisson. Here it's just, I'm just going to give you like an overview of it. And then move into some continuous distributions, uniform, Gaussian, exponential, and if there is time, we'll do power as well. Otherwise, in the next class, I'm planning to do power, and then we have a few remaining topics, some rules, theorems on limit, on amount, on bounding the tail probabilities of distributions, and then the joint probability and the Bayesian networks. Okay, so let me just start with the first topic, geometric. So a geometric distribution is a discrete distribution. So what it is it has to do again with trials. So generally speaking, when you have discrete distributions, it has to do something with some kind of trial going on. In this case, what you're looking for is the number of failures before the first success. So remember, we have Bernoulli trials. So in a Bernoulli trial, we have probability P of success, and then probability 1 minus P of failure. And when we do binomial, we're talking about the number of trials that we want to do. So I should say, take it back. Binomial, looking at the probability of having, certain number of successes. Let's say you do 100 trials. How many of them are likely to be successful? Let's say you want to say 8 successes out of 100. That would be binomial. We're assuming independence. This is very important. Independent trials. Again, this is something that doesn't always hold in practice. And the reason why it doesn't hold in practice is because independence means that you do the first trial and there is no effect on the second trial. But in reality, the conditions that lead to the first trial very likely hold for the second trial as well, right? So let's say you're, the testing for the amount of humidity in the air, and you do a trial at 9 o'clock. Now you're assuming that the next morning when you do the trial, these are independent events. That's humidity, whatever the value is, it's an independent event. But of course, the weather system that lasts 3-4 days is going to make them correlated. So while we make these independence assumptions for the math to be nice, in reality, independent trials doesn't always hold. And one of the things you really have to be watching out for when you do any kind of study or any kind of research is, are these things actually independent or not? So that's one of the things you have to worry about. Anyway, so assuming they're independent, we essentially have the following situation. You have sort of a failure, and then a success. Okay, and you can have certain number of failures and then a success. Now the failure happens. So okay, to come back to this. Okay, what I wanted to say was, so geometric trial is the number of failures before the first success. That's what you try and capture. In other words, binomial is how many successes happen if you do so many experiments. Here I'm saying, okay, I'm going to have these failures. What is the first time we get a success? So it's starting at the beginning. So we start at this time, move forward, we get a failure, and a success. So there's 1 minus P, there's 1 minus P, and so on. And then you get probability success as P. And because these are independent events, we can multiply them out to get the total probability. So we get the probability of I. That means that we have the I failures and the first success. Another way of thinking it is that the ith trial is the first successful trial. Okay, that's the way to interpret that. Probability that ith trial is first successful trial is just nothing more than 1 minus P to the I and P. So that's your classic geometric distribution, and so this kind of gives us the formula. There's not a whole lot to say about this, and probably it's easier to understand what's going on with an example. So let's 10 minutes. Oh, I'm sorry. Yeah, I minus 1. Right. Yes. Because you have I minus 1 of these, and this is the first one. So let's say we have a link. So this often shows up in networking in the following context. We have a link, and the link has a packet loss rate. How do we get the packet loss rate? Let's say we take the frequentist approach. We send 1 million packets, and 100,000 of them get lost. We'll say it's a 10% packet loss rate. So it's and so we can express this, the loss rate, as 0.1. Now what I want to do is, what is the meaning of a success? The meaning of a success is it gets to the other side. Meaning of a failure is it did not get to the other side. So in this case, 0.1 is the loss rate, and it's sort of the opposite, right? Here, the event happening is loss happening. So instead of the packet failure is an event success, and event failure is a packet success. So what I mean by saying is that 0.1 is the probability of packet loss. Okay, so we can represent it as either P or 1 minus P as you wish, but let's just say that this is nothing more than 1 minus probability packet success, and so it's easier for us to deal in terms of packet successes. So probability of packet success obviously is equal to 0.9, so it's just 1 minus the loss rate. So that's easy. So what I want to do is to find out how many times you need to send the packet over before it actually gets to the other side, right? So I send the packet over, it gets lost, I read timeout, I retransmit, I send it over, etc. I want to find out how many times I need to do it. So probability that it gets through the first time is what it is. P1 means first trial is successful. So that means I just sent it over once. Well, that's nothing more than 0.9, which you get from by plugging in the formula over here as well, okay, because I is 1. And then P2 is 0.1 times 0.9, which is 0.09, okay, and P3 is 0.009, etc. I mean, you can keep doing this, and you can see right away that if you send the packet once, it only has 90% chance of making it. But if you send it twice, you're going to have a success rate. Oops, what am I doing over here? Yeah, right. So the probability that I need to send it twice to make it through is only 9%. Okay, 90% chance it got through the first time. I need to send it twice only 9% of the time. Probability I need to send it 3 times is even less. It's 0.9%. So the probability that I have to send it, let's say 10 times is infinitesimally small. Okay, so even the 10% loss rate, if these are independent events, it's very likely that I don't have to send it very many times. Okay, that's really what's going on. So the expected value of the geometric distribution with parameter P, okay, is expected value of X. Let me just be careful here. So let's say X is geometrically distributed with parameter P. Then expected value of X is 1 over P. Okay, so in our case, P is 0.9, so expected value of X in this case equals 1 over 0.9, which is 1.1 bar. So basically we're going to have to, or we expect to send it roughly like 1.1 times. Okay, on average that's what we expected to send, so a little bit more than once. This is a very interesting result from a perspective of packet transmission. It says that even though we have 10% loss rate, which is considered fairly high, we just had to send a little more than once, 10% more, roughly speaking, 11% more, and we'll actually get it through to the other side. And this is why, at a gut level, this is why timeouts and retransmissions work. Okay, the reason it works is because you time it out, you send it again. If the events are independent, it's a pretty good chance that the second time you're going to get through. Okay, so the first time you're getting it through only 90% of the time, but second time you're probably going to get through because the expected number is only 1.1. Okay, so this is really where that kicks in. Now, I mean, the condition over here is independence, and this is again where the weak point of this analysis is. If you have a congested network, you send something in, chances are the congestion persists for a certain amount of time. Let's say it persists for a few seconds. So you send a packet, you time out, you send it again. We don't have an independent trial. The packet loss rate stays high for a reasonably long period of time, so we cannot apply this result anymore. So naively you'd say, yeah, these are independent events, and so I can do it. Same thing is true for wireless links. If you have a wireless link, it has a link loss rate of, let's say, 5%. You'd say, great, if I send so many, the link loss rate is going to be very low. It's only 5%. I'm very likely going to have to only send 1 or 2, and you expect that the first transmission and second transmission are independent. But if you think about it, why did you lose packets in the first place? It's because maybe you went, on the side of a hill, and you're driving on the side of a hill. You're going to stay on the side of the hill for a long time. So analysis which assumes that these packet probabilities are independent, okay, are actually not going to work. So you can do all the math, you can say, well, the expected retransmission rate is only so much, but in fact, what you're seeing here is bursty losses. You have a loss, then the probability of a successive loss is actually quite high. And you can have 3 losses, 4 losses. So in this case, what you really have to do is to choose the timeout and retransmission so that when you retransmit it, you're outside the previous event, whatever that event is. And so there is a concept of the time scale at which the link is bursty. Okay, you want to time out and retransmit things after the time scale at which these congestion events or loss events persist. So the point I'm trying to make here is that when you look at the geometric distribution, you compute the expected value. Just looking at the math, it looks pretty straightforward. Yeah, sure, it's only 1.1. But when you start looking at the system and the underlying reason why loss happens, you have to think a little bit deeper about this. You can't just blindly plug in the value and use it. You have to think about it. Okay, and that's what is the difference between studying a geometric distribution in an undergraduate class and then studying it here. Here you want to think about, is it really true? What's really going on? Okay. Okay, let me take any questions about this. Yeah?
But by changing the event, aren't you actually changing those probabilities?
I'm saying that the assumptions of the geometric distribution may not hold because these are not independent trials. So what's happening is that the conditional probability of a loss, condition on the fact that there's a loss, let's say there's a loss at time t, conditional probability of a loss at t plus delta, where delta is small, is actually higher than the unconditional probability. That's what I'm saying. So if you don't do anything, you'll say probability of loss is 10%. But if somebody says at time t equals 5, there was a loss, and at t equals 5 plus delta, you're going to have a higher loss rate than 10%, maybe 90%. Okay? So you have to model that. You can't just plug in a geometric and just say, look, I plugged in geometric, I chug away, I get this 1.1, I'm done. Okay? It's not going to work. Okay? So that's what I'm saying. Any other questions about this? Okay. Yes, Omar.
Is P the probability of success or is it the probability of...
P is the probability of success.
But it's going down.
No, this is not. The probability of success is not going down. Remember, I have to interpret. Capital P of 2 is probability that the ith trial is the first successful trial. So if P is large, right, it's going down very fast because I don't have to wait very long before I get the first successful trial. So let's say P is 0.999, then P of 2 means, do I have to do it twice to get the first success? No, I don't. I'm probably going to get through the first time. So as P gets larger and larger, closer and closer to 1, the number of trials I need in order to get its first success goes down. Okay? Or the probability that I have lots of failures before the first success goes down. That's why I wrote this out over here, because I'm using P twice and it's a bit of a problem. Starting with the Poisson, we'll move from P to lambda and then life is better. And in the lecture notes, I changed the notation to lambda for the Poisson distribution for that reason. It got too confusing. But for whatever reason, in the literature for geometric, people use small p for the parameter. They don't use lambda. Okay. I mean, why do they do that? I don't know, but that's what they do. And I don't want to. So I'm going to keep you equivalently confused, not extra confused. Yes, you had a question or no? Okay. All right. Let's move on to the Poisson distribution. Oh, I should have left it up. Oh well. Okay. Okay, so the Poisson distribution arises in many different contexts, and as I said, we'll study Poisson in some detail when we study what are called pure birth processes. But here what I want to do is to motivate the Poisson purely as a convenience tool to calculate binomial probabilities. So let's go back to binomial for a minute. So we said we have the Bernoulli trials, and with parameter small p. Now, and also I have something called the number of trials, which I call n. And basically we had the formula that the probability that x equals I is nothing more than n choose I, p to the I, 1 minus p, n minus I. Now this is easy to write, but it's kind of hard to compute when n is large, because you have the combination, we have this one over here, n choose I. For example, if n is, let's say you do 1,000 trials, n is 1,000, and I is, let's say, 200, then you have to compute, so 1,000 factorial by 200 factorial, 800 factorial. And, okay, you can kind of take this out by subtracting it, but still you have a fairly large number of computations to do. And you're saying, boy, this is a pain in the neck. Is there a way to get around this? And the answer is yes, you can get around this. And the way you do it is to use the Poisson. So remember what we have with the binomial, if you think about it, is you have some kind of distribution, a histogram, if you will. You have some central mass, and then it's a little bit symmetric. What I'm going to do is I'm going to show you two different ways of computing these values. Okay. In the first case, what we do is we retain the I as being discrete. So the probability of I, that means you have I successors over here. So Px equals I means we have I successors. We're going to compute the probability of I successors, but we're going to essentially use this trick to compute this very easily instead of having to do all this computation over here, and that's the Poisson. And the second thing what we're going to do is we're going to take the number of trials, n, as going to infinity. Okay, we're going to infinity. What that means is that then we get a continuous distribution. Okay, when you get a continuous distribution, then it turns out that we can use a different formula, and that is the normal distribution. Okay, so there are two different ways in which we kind of are looking at the approximation to binomial. Okay, so what I'm going to do here is that I assume that we can represent by lambda the product of n and p. Okay, so if n is large and p is small, okay, we need to kind of, I'm not saying how large it is or how small p is, but we can kind of just say n is large and p is small. Then we take the product of np, and this is called lambda. And in some sense, this is the overall probability. Let's say you do 1,000 trials and probability of success is 10%, then you expect about 100 things to be successful, right? That's roughly speaking what you want, what you expect to see. So that's kind of NP, that's what your lambda is, okay? And so what we're going to do is that we are going to write down the Poisson formula. So the probability that we have x equals I, that means we have I successors, can be written instead of this way, we can write it as e to the minus lambda to the I. I don't need the parentheses actually. Lambda to the I by I factorial. Okay, so we haven't got rid of the factorial completely, but at least it's a little bit less cumbersome than this. And it turns out that this approximation of the binomial is quite accurate. In the homework exercises, what you have to do, and I'll come to homework when you do the administrative break, is that you compute the binomial and the Poisson for small value of n, large value of n, and you'll see that when you have small value of n, they differ quite a bit. But when you have large value of n, actually they come very, very close. It's quite close. So that's one way to understand Poisson. Again, as I said, there are many different ways of understanding it. But to be more precise, so what we have over here, so if you ignore the binomial for now, what we're going to say is that we have a discrete variable, a discrete random variable x, and it has the domain is now it's infinite. Okay, remember that in the case of the binomial, we have n trials, so it's sort of a finite domain, but here we have 1, 2, 3, etc. It's an infinite domain, and it is it has it's Poisson if the distribution looks like this: probability x equals I e to the minus lambda, lambda to the I by I factorial. Why does it look like this? We'll come to that when we discuss queuing theory, okay? Because then the intuition becomes very clear. For now, all that's important is this is the form. This is what it is, okay? And it turns out that another intuitive way of understanding is like this. Think of the following thing: I have a switch or a router, and then I have I have a bunch of sources that are sending inputs to the switch or a router. And now what I'm going to do is that each source has some intrinsic probability. Let's say there are n of these, and each of them has some probability p of sending a packet into this router. Okay. What I want to do is I want to find out what is the probability that I packets arrive to this router in any particular time period. Again, what we can do is we can say, okay, these are independent trials, and so we can compute the probability that I packets arrive, okay, where p is the probability over some time period that a node sends some data. You can compute over that same time period the probability I. You can define that as a Poisson. So as a more specific instance, consider how the University of Waterloo is set up in terms of its routing. So we have different builds. So the way it's set up is that on campus we have 30 buildings. Each building has a access kind of wired closet, and then through that wires go to every room. Okay, and then a bunch of actually what I call wiring closets, just these small rooms. You open it up, it's full of wires, and from there wires go to every office and to labs and so on. Let's consider what happens to all these buildings. They all actually go through gigabit links to a router that's in the basement of this building. I'm probably standing right above it right now. Okay, there's one box over here in the basement of MC, and that's the main campus router, and this has some output link. Actually, you have two links going to two different networks. In case one goes down, you can switch to the other. But that main campus router is below us. Imagine these terminals are, in fact, the endpoints, all the PCs and laptops, etc., in the entire university. Okay? So what I want to do here is I want to model what is the total traffic coming into this router. Again, if I have some way of measuring the probability that over a period of, let's say, 1 minute, a node sends data, okay, and this could be different from different times of the day, that's fine. And these are independent. I assume that people aren't all going to things at the same time. Again, independence is important. Then I can model the traffic coming in over here as a Poisson distribution over here. Okay, and so this assumes that everything is independent, etc. Okay, so because of this, the Poisson distribution is very commonly used in analysis of networking systems, because we typically have lots of sources, and the typical usage ratio of any individual node is fairly small. So until about 1995, this was like the standard, the golden standard. If you want to simulate a network, you assume Poisson process coming in, you choose the intensity by choosing lambda, and then you kind of get the stuff coming in. Around 95, people said, look, is it really true? Is it really Poisson? And in a series of papers, two researchers, Vern Paxson and Sally Floyd, actually started measuring lots of different nodes, and they wrote a classic paper called The Failure of Poisson Modeling. Okay, basically they said, look, all these models assume Poisson are wrong, because traffic is not Poisson. And they showed that while we can assume these things are independent, etc., in reality it doesn't work. Everything that you look at is non-Poisson. These are not independent. Just to give you a very simple example, we say that that these are independent events. It means that if somebody here decides to send data, it's unlikely somebody else is going to send data at that same point in time, because you have these ratios. However, we have lots of correlated events. For example, this class is, people are in session, nobody's using the computer right now. However, when the class is over, everybody goes to their office, immediately there's a surge of traffic. Okay, or if you look at, people come into work, at some point, if everybody comes into work, then, there's correlated events. Some news event happens, there's correlated events. So in fact, we find these independence assumptions don't work. So while Poisson is nice and it's in queuing theory, it's actually essential to do anything reasonable. We'll see that. It turns out that in practice it doesn't work. So I'm showing you sort of both sides of the Poisson coin. Okay, on the one hand, it's nice, it's intuitive, it looks pretty good, and it certainly models the binomial, but because independence isn't true in practice, it doesn't work. So you need to know when to use Poisson. Poisson is useful as like a first cut. Okay, you don't exactly know what's going on, what the traffic is. You haven't measured it. You'll say, okay, let's assume Poisson. We'll get some numbers. These are likely to be off by a factor of 5 or a factor of 10, but at least it's not off by a factor of 1,000. Okay, so that's kind of a rough and ready analysis. You use Poisson. Okay. All right. Any questions about this at all? Yes.
So the x in this case, in the Poisson formula, is the number of trials, right?
Number of trials that succeed.
That succeed.
Yeah, equivalent to how many packets arrive over here.
Okay, no. So isn't it the number of failures and then I would be the successful?
No, that is geometric, right? In geometric, we say how many successes, how many failures before the first success. In binomial, which is why I started over here. Binomial, we say I have number of trials n, and probability of success of each is p. I want to compute probability that we have I successes among the n is this formula over here, right? I have to get p to the I successes, 1 minus p to the n minus I failures, and that gives me probability of I successes. And then I'm approximating that over here, and still I have p x equals I. I want to know what is the probability that we get I successes in this. In these trials, but of course we have in this case sort of infinity of trials, but with discrete points. And in the, as I said, in the Gaussian we have a continuous distribution. There's a discrete distribution. Any questions about this here? So let me do a small numerical example just to kind of drive this home. So let's say we have 1,000 endpoints. And we know the probability p is 0.001 that they are going to be active. This is just like at MC, so we have 1,000 servers that are sending data to this router, and any one of them is active at 0.1% of the time. Then we can say lambda equals 1 because you just multiply these out. And now I want to know what's the probability. Let's say that this is 0.001 in any 1 second. I'm giving the time period now, interval. Okay, so the probability that what's the probability, let's say, that we see at least one, okay, so what is the probability we see at least one packet in 1 second, right? So at least one packet at R is nothing more than 1 minus P of 0, right? Probability x is 0, so it's just probability 0 packets is nothing happens, and so 1 minus this. So this is equal to 1 minus, I just plug in the values. It's e to the minus 1, and then lambda is 1, so 1 to the 0 upon 1 factorial. So it's just nothing more than 1 over 1 minus e, which turns out to be 0.64. So there's a 64% chance that we'll see at least one packet, okay, with parameter 1. With lambda equals 1. So 64% chance that the link is not idle. Or you can say even with 1,000 nodes and lambda is 1, there's a 36% chance the link is actually idle. If I just look at it for 1 second, I can just plug this in and get it right out of that. I mean, of course, I can assume it's Bernoulli, etc., and go through binomial and go through that whole thing. But if you use the Poisson, this is what you get. Okay, and there's I think one other example in the homework that you should probably try. I should add that even though here I've said that Poisson comes in when the trials are independent, there's something called weak dependency, which I don't fully understand. And the claim is that even with weakly dependent events, you still get Poisson. which is great, but as I said, in practice, nodes events are strongly dependent, and so we don't actually get Poisson, but it's a good rule of thumb to use. Okay, any questions about this over here? Yeah.
Anything suggested about all this real world traffic, one which is correlated, any model or anything?
Yeah, people have proposed a number of models. Most widely used what I call long range dependent models, and where they show that we don't have independent, but we have dependency over a certain number of previous events. They define what's called the autocorrelation function, and they look at the degree of autocorrelation over various lags. Okay, the problem is that these are not analytically tractable, so you can use them for load generation. Okay, you can come up with power law or these long-range dependent traffic models, but I can't tell you anything about the output other than by simulation. So in other words, I have this input coming over here. Well, I didn't tell you what the router service rate was, but let's say I choose some service rate. Okay, let's say I can serve a certain number of packets per second. What I want to know is the queuing behavior. Okay, with Poisson I can tell you the queuing behavior. I can tell you the probability of how many packets are going to be in the queue and the distribution. All right, I can tell you exactly the probability of that. And that we'll study that, in about 2 weeks' time. But with these kind of realistic traffic models, all I can do is simulate it. And then there are many different parameters, how to choose these different things. It gets very messy. So, yeah, we don't actually have at this point analytical tools that allow us to compute parameters of interest for these kinds of traffic. So if you're doing simulations, you can use these, what I call LRD, long-range dependent models. Yeah. Any other questions? Okay, let's stop here, and then, I guess I'll continue with the uniform. So let's see, I had a couple of announcements to make, the discrete distributions to continuous distributions. And just to remind you, in the discrete distribution, we compute the probability Px equals I. That is, we have some discrete domain which is indexed by I, and we're computing the probability mass function that you have this value assumed by the variable x. And in some cases, it's the number of successes. In some cases, it's the number of trials to the first success. But we have a number. We have a number of x, number of something. Okay. In the continuous case, we have basically probability that x equals x. This is not really a probability anymore. So we don't want to actually use that x equals x at all. What we instead say is that we have a density function. And again, I've revised the notes just to keep it consistent with standard terminology. I'll call it fx. Okay, and I don't want to use the word p there because it's confusing, as we said earlier. What we can say is that the probability that x1 is less than equal to x less than equal to x2, should make it capital X. The random variable x lies in the range is x2 to x1 to x2 fx dx. Okay, so that is the only definition we're going to get in continuous, which is that we can talk about the amount of probability mass that lies in some interval x1, x2. Okay, so that's kind of what you need to understand going in. All right, so we're changing our mindset from probability mass at discrete points I to probability mass in the interval x1, x2. Okay. All right, so just to get it clear, let's start with uniform. So uniform is kind of the simplest continuous distribution. What we're saying over here is that we have in some interval a, b, we have uniform probability mass. Okay, how much mass do we have? What is the value over here? Okay, what is that? This should be easy. 1 upon b minus a, because we need to have the total area under the curve to be 1, right? So it's not like the probability of any value over here is b minus a, 1 over b minus a. In fact, we don't have that, but we can, of course, what we're saying is that this holds over here. So this is basically all there is to it. The expected value of x, where x is distributed uniform, is b plus a by 2. This is trivial to show, and sort of fx equals 1 over b minus a. Okay, that's the value of x at any point is 1 over b minus a. I'm just drawing that over here in the range. A less than equal to x less than equal to b. Our old friend, the 0, 1 uniform is just a equals 0, b equals 1 over here. Okay, all right, so this is mostly for you to sort of switch your thinking from discrete to continuous. So let's start with the first non-trivial distribution for continuous, which is the Gaussian, or normal as it's called. So the Gaussian distribution, the